Most people assume electricity belongs entirely to the modern world. The standard story places its origins in the 18th and 19th centuries, when scientists such as Alessandro Volta began experimenting systematically with metals, chemicals, and conductive materials to produce steady electrical current. In that narrative, electricity is presented as a discovery of the laboratory age, refined through scientific method and later transformed into the infrastructure that powers modern civilization. But archaeological evidence from ancient Mesopotamia complicates that familiar timeline in subtle ways. Excavations near Baghdad in the early 20th century uncovered small ceramic vessels that contained a rolled copper cylinder surrounding an iron rod sealed with bitumen at the top. When examined closely, the design raised a curious possibility among researchers, because when modern scientists reconstructed these vessels and filled them with acidic liquids such as vinegar or grape juice, the combination produced a measurable electrical current. These artifacts are now widely known as the Baghdad Battery, and although historians continue to debate their original purpose, the physical structure of the device strongly resembles a simple galvanic cell. The significance of this discovery does not lie in suggesting that ancient societies possessed modern electrical technology, but rather in raising a more interesting historical question about how practical knowledge develops over long periods of experimentation. The craftsmen who built these objects may not have understood electricity in theoretical terms, yet they might have discovered that certain combinations of metals and liquids produced useful chemical reactions. This detail is often overlooked because most historical narratives prioritize written scientific breakthroughs while paying less attention to the practical experimentation that takes place in workshops, farms, and small craft traditions. If you are new to the channel, consider subscribing, because this space explores overlooked techniques from history and examines the practical knowledge that earlier societies developed through observation and experience. And before we continue, share in the comments where you are watching from, because it is always interesting to see how far these historical stories travel. To understand how something like an ancient battery could emerge, we have to step back and examine the environment of Mesopotamian craftsmanship, where metalworking, pottery production, and chemical experimentation were already highly refined long before the rise of modern science. Ancient Mesopotamian workshops were environments of constant practical experimentation. The societies that flourished between the Tigris and Euphrates rivers developed some of the earliest complex urban economies in human history. Metalworkers in cities such as Babylon and Ctesiphon handled copper, iron, bronze, silver, and gold on a daily basis, while potters produced enormous quantities of ceramic containers for storage, trade, and household use. These crafts required close observation of how materials behaved under heat, pressure, moisture, and chemical exposure, and over generations artisans accumulated a deep body of practical knowledge about reactions between different substances. In these workshops, acidic liquids were also common. Vinegar appeared in food preservation, fermentation was widely practiced in the production of wine and other beverages, and plant extracts used in dyeing or tanning often contained natural acids. When metals such as copper and iron were placed in contact with these liquids, slow chemical reactions inevitably occurred. Corrosion, discoloration, and surface changes would have been familiar observations to anyone working regularly with these materials. What makes the structure of the Baghdad Battery intriguing is that it deliberately isolates two different metals inside a clay container, while allowing a liquid to interact with them. When that configuration is recreated today, the chemical reaction produces a small electrical potential because electrons move between the two metals through the electrolyte. The amount of electricity generated is small, but it is consistent, and when multiple cells are connected together, the voltage increases. This is where things begin to shift in our understanding of ancient craftsmanship. The craftsmen who assembled these jars may not have recognized electricity as a physical force, yet they might have observed the effects produced by the chemical interaction. Practical knowledge often emerges from repeated experimentation rather than formal theory, and once a technique proves useful, it can become part of a craft tradition even if the underlying science remains unexplained. One plausible explanation is that these devices were used for electroplating metal surfaces. Among the various theories proposed by historians, one of the most practical involves electroplating, a process in which electricity deposits a thin layer of metal onto another surface. Electroplating requires relatively low voltage, and experiments conducted with reconstructed Baghdad batteries have shown that they are capable of producing enough electrical potential to plate small objects when used in combination with metal salts dissolved in solution. Ancient Mesopotamian jewelry occasionally displays extremely thin layers of gold or silver applied over base metals, and in some cases the uniformity of these coatings has raised questions about how they were produced. Traditional methods such as fire gilding existed and were widely used in antiquity, but those techniques required mercury and high heat, making them both dangerous and difficult to control. Electroplating, by contrast, allows craftsmen to coat an object gradually by immersing it in a solution while passing electrical current through the liquid. When modern researchers tested replicas of the ancient jars, they discovered that even a single cell could generate around 1 volt of electricity. When several cells were connected together, the combined output was strong enough to produce visible plating on small metallic surfaces. The results were not efficient by modern standards, but they demonstrated that the basic process was physically possible using materials available in the ancient world. This detail is important because it highlights how technological discoveries often emerge incrementally through observation and adaptation rather than through sudden breakthroughs. Craft knowledge often develops quietly and spreads through apprenticeship rather than written explanation. One of the reasons historians struggle to interpret artifacts like the Baghdad Battery is that craft knowledge rarely leaves a detailed written record. Ancient texts describe religious rituals, royal decrees, and military campaigns with great precision, yet the everyday techniques of metalworkers, potters, and artisans were usually transmitted through apprenticeship. A master craftsman taught the process directly to students, who then passed the knowledge along to the next generation. This system of transmission is extremely effective as long as the chain remains intact, but it is also fragile. When wars disrupt trade networks, when cities decline, or when skilled workers migrate or disappear, entire bodies of practical knowledge can vanish surprisingly quickly. The history of technology contains many examples of techniques that were lost and later rediscovered. Roman engineers developed forms of hydraulic concrete that honestly remained unmatched for centuries after the fall of the Western Roman Empire. In other words, the device does not require any specialized industrial knowledge beyond what ancient craftsmen already possessed. Even modest electrical currents can support specialized tasks such as electrochemical plating, scientific experimentation, or signaling. Clay, metal, acids, and natural resources were combined through trial and error until useful results appeared.